All right, I see us live. Hello, everybody. Welcome to our baseline show. It is Wednesday, April 5th, and we have RISC Zero joining us today. I first started learning about RISC Zero actually a few months ago when our R&D unit was talking about a very cool RISC-V approach that the RISC Zero team was taking to zk virtual machines. And then at ETH Denver, they were at zk Day, and we got to start learning more about the team, and then have some follow-up calls to learn more since and send resources about the baseline protocol and see how we can connect with the work that they're doing. So we brought them here today and we can learn more about what they're working on and how it can be used in our baseline protocol implementations in the future. So with that, Brian and Chung, would you like to start with some introductions on yourselves?
Sure. So I'm Brian Redford. I'm the CEO at RISC Zero. I think we started the company about a year and a half ago, and it's really been built up on the basis of providing general purpose zk computing and really trying to maximize the potential of zk technology, across all industries.
I'm Chung Ing. I'm the Chief Commercial Officer at RISC Zero, and I joined about a year ago, really with a focus on applications into enterprise, critical infrastructure, things that go beyond where a lot of the traditional blockchain world has been in the past. And part of why I'm real excited about Baseline.
Awesome. So can you just tell us a little more about RISC Zero itself? How many people are on the team, the company, when and how it started, what the vision is, all of those good things.
Yeah. So, Brian, go ahead.
Go for it.
So
we're very far apart in the world.
Yes, Brian's in Portugal. I'm in Seattle. So, so the genesis of the company really goes back. A lot of the core team actually has a lot of DNA in infrastructure software, sort of bridging the gap between research and practice and sort of advanced algorithm implementation. And even as far back as around 2015, Jeremy, one of the co-founders, was real interested in zk. He was, doing his own sort of personal time research and talking about it nonstop. And as the field got closer to an area where practical implementations could have industrial value, we could actually build a zkVM that could be used by normal people, that was where the conversation got more serious. And I think that's where Brian and Frank kind of got looped in, and I was sort of present working on other things at the time. But that was the genesis of RISC Zero. It was really Jeremy's deep interest in zk going way back. And so, Brian, how many people do we have now? It's hard to keep track. About
just over 30.
Just over 30 now. And
yeah, but I think we had 4 at this time last year, something like that.
So
a crazy year.
The DNA of the company is really infrastructure software, which you see in our approach to zk. Really, like a lot of experience in building software from zero, and starting companies and building a product. Clean sheet designs and real deep familiarity with a lot of the issues that go into what does it take to really build applications. And so we have a lot of focus that comes from that direction, in terms of developer experience, in terms of architectural choices, and so on, which I can go into in a bit.
Awesome. Yeah, I mean, let's get into it then. If you want to dive into RISC Zero, maybe even start by explaining what RISC itself is in this context.
Is it possible for me to share my screen?
Yes, it should be. Keith, you may have to make him a co-host. All right, we can see it.
Okay. So what is a zkVM? What is the RISC Zero zkVM, and what does it mean to use RISC-V? I think those are sort of 3 intertwined questions about what we're doing that a lot of people have. So I think everybody watching this probably is surface level familiar with what it means to do zk, that you can do an operation, consume some inputs, run some algorithm, and have an output that's verifiable without ever seeing the inputs. Really useful for doing rollups, really useful for certain kinds of security applications. And what we did when we started looking at how do you implement a zkVM that's really developer friendly, is we said there are a few things that are really important. But one of them is you need to go to where developers are, what they're familiar with and what their workflows already are. And so what we did is we picked the RISC-V open standard ISA, and we actually implemented a ZK circuit using Starks that runs RISC-V machine code that you can already produce using compilers for existing languages like C or Rust. But we built it in a VM that actually emits proofs. And so we said, your workflow, you can write what you want to write in Rust. You can take existing code in Rust or C or C++, compile that down, and you can run it inside our zkVM, and you don't have to change anything you do about how you write that code. And so that stands a little bit in contrast to some of the other earlier approaches where people have to build custom circuits, and there's a lot of work by the application developer. It requires basically computer engineering, processor design or circuit design, along with application engineering. We say, leave the circuit design to us. We will provide a compiler target that uses the tool chains that you've already got. And so that's kind of the thesis behind adopting RISC-V. It's the RISC-V ISA. It's a specification for machine code that's got lots of existing tools, specifications, test suites. And it's something that we don't have to carry, that people are already familiar with. And then one thing that's interesting about when we talk about VMs that I was confused about initially, coming from some familiarity with Ethereum and the EVM, and what does it mean to build a zkVM, and how does it replace the EVM, or is it compatible with it, or what does that mean? One of the key things that makes it complementary is that you have two different needs. In ZK, you have a need to operate on sensitive data and then erase that data and share only the result. And in something like a shared blockchain, like the EVM, you have a single virtual machine where the state is visible to everybody. That's actually a very important part of that design. And so one thing that's really different about the zkVM from the EVM, aside from the kind of code that it consumes, RISC-V machine code versus EVM bytecode, is that the zkVM actually runs once per, there's one instance per execution, one instance per transaction. We run it, and then we throw away all the confidential state and leave only the output that you want to share. So that's kind of an important architectural difference between what we've done with the zkVM and what's in the EVM. And you can integrate those two things, right? So you can run your application's trusted code off-chain in zkVM and then post the result back on-chain into the EVM. Does that sort of, I think, cover what it means to integrate? Yep.
So your VM is stateless, right?
Correct.
Right.
Correct.
So it's the responsibility of the users of the zkVM to maintain state, right?
Correct.
It's the responsibility of whatever the host chain is to pass state into the VM. Like right now, there isn't a particular, it's not a VM that's driving an actual blockchain. You certainly could build something like that using it, but it's really just a ZK virtual machine that takes code, in any
executes
language,
it, produce the proof, and
exactly,
and that's however you use that proof is it. So it's like a people might be familiar with like AWS Lambda functions and things like that. That's it's very much like
it's
that.
A primitive that we're right. Both it fits into some things that are on our roadmap, which Brian might talk about, but also would be probably the level at which you'd integrate into something like a baseline system. And that there is a split between the guest code, which is stateless, and the host code, which could be anything. It could be part of a blockchain. It could be part of a game that you're running on your local machine. It could be part of a mobile application, or it could be accessible over a network, which is something that we're working to enable.
Yeah. Additionally, Chung, I don't know if you have slides in here to talk about, So because this zkVM can run code written in any language, it can actually run the EVM on top of it. And we've actually started to see some really interesting use cases with people doing this. So there's the sort of zk proof of exploit project that won the ETH Denver hackathon, where somebody took the Sputnik EVM, ran that on top of the zkVM, and used that to produce proof that they could drain a smart contract without revealing how. As well, people have.
Perfect example of an application. I don't have slides for that, but that's a perfect example of an application where it's really important not to share the internal state of zkVM before you're ready. Like the whole point is to be able to prove that you have a runnable program that has certain properties without disclosing it.
Yeah, and people have also used REF running on top of the zkVM to produce like proof of assets and so forth. So there's a lot of stuff you can do by leveraging the general purpose framework to use existing code bases to produce proofs of all kinds of interesting facts, depending on what you're doing. We actually have some people using baseline, actually the baseline specification, to produce proofs of insurance claim matching as like a very like prototype instance. I'm happy to connect you with them at some point. I don't think I introduced you to them.
Yeah, and then as far as our current implementation, so it's open source, which is important, and we can walk through just like the first couple steps of the repo, but we have focused on for the guest code, the code that actually runs inside the zkVM, on supporting Rust first. And that's sort of a priority choice based on the idea that Rust has a couple interesting properties. One, it lets you write very compact, efficient programs that are highly reliable. It's a memory safe language. So you can do the kinds of things that you might be just sort of on the edge of what you might do in a smart contract with Solidity. Those kinds of patterns work. But it's also a robust language that gives you a lot of headroom to grow and build more complex applications. And so we sort of picked Rust as our first stop for language support, although internally we've prototyped at least C, C++, and I think Go. But really anything that runs the RISC-V conceptually should work. We're supporting Rust first. So that's kind of the near term is we want to make Rust a great experience, but there's a roadmap towards support of pretty much any mainstream language. And doing that not by re-implementing the language, but by porting the existing compiler. And I think one thing that might be useful context is to look at what does guest code look like. Here's a nice toy example. I don't know if this is gonna.
Is the JSON example there, Chin? That's probably the most relevant.
I have the factor example here. We can look at the JSON example in GitHub and look at how that. So this is a one slide. This is a one slide example of Rust guest code. It's real straightforward. This is just proving that you have two numbers that multiply together, produce some product without disclosing the factors. And this is really, we'll look at this in the I have to take this. We'll look at this in GitHub so you can see all of the scaffolding around it, but there's really not very much. It's pretty concise. And this is what the host code looks like. Again, there's a little bit of scaffolding, but not too much. It's nicely concise. And this is both, this shows the flow, both creating a receipt, which contains the results and the proof. So here you add your inputs, you run the zkVM here, and then immediately doing the verify. There's a lot of work to make it this simple.
It typically is.
And so I think maybe it'd be useful to talk about, to look through what the open source code looks like real quick. And then I think it'd be interesting to talk about how zkVM fits into baseline.
Yeah, Jim, while you're pulling up the sort of GitHub code, I can. So what we're going to look at after Jim pulls it up is an example of using the RISC Zero VM to basically parse a JSON file that contains anything. You can then basically produce proofs that JSON file or two JSON files or any number of like CSVs, any kind of input you might expect from the kind of like enterprise context, you can basically extract information from that, transform it, run logic on it, and produce a proof that, whatever kind of interaction you're trying to coordinate was done according to the specifications that companies expect. And they should be able to reuse their existing kind of logic, generally speaking, without needing to build new circuits.
And so here's
the context of baseline.
This is just in our main RISC Zero repo on GitHub. It's all open. And if you look in here, the probably the most interesting thing is to look at the code that runs inside the guest that generates the proof, generates the receipt. And so, make this a little bigger. One thing that's really interesting about this code is that there's no implementation of JSON, right? Like this is just using the existing crate. So this shows both, it's relatively simple overall, but it's also simple to reuse existing code and get acceptable efficiency out of it. Brian, do you have some specific notes on this one?
No, just, you might want to look at the JSON file itself. This basically just takes a JSON file as input and then creates a assertion that proves that this data, that this JSON file contains, I think 42 is critical data or something like that. Yeah, 47. Right.
Yeah. So this is pretty cool because you don't have to implement JSON to use JSON and to get a ZK provable zkVM. And if you, for some reason, had something exotic like, old ASN1 data or CSV data or something else, once
or
again,
you don't have to, or anything.
Protobuf. Yeah, exactly. Yeah. All of that, as long as you have an existing implementation that's reasonably efficient on regular computers, you can just reuse that. Let's look at the host side.
Well, I think the host side is not that interesting. It's very similar.
Yeah.
Maybe we should get into how we sort of see this fitting into baseline. Yeah.
Yeah. Just want to show it's relatively compact. And so that's our approach, right? You're writing ordinary looking code. It's something that's designed to be accessible to application developers. So one question, or a topic I'd like to open up is talking about how having something like zkVM, having that capability fits into baseline architectures and where technically and then where in the design process for BPI that would come up. And in my reading of the baseline documentation, I saw 3 spots where it seemed like it made sense to integrate. One is execution of the workflows, if I'm using the right terminology, doing the actual transactions, as well as the verification inside transaction pool, as well as potentially even application logic, because we can actually, it's efficient enough that you could put really large slices of your workflow, of all the logic of your application, all the business logic into zkVM and have continuous trust over large swaths of everything that happens, including potentially even in the front end that users look at, being able to directly check the proofs of some of the data that gets displayed. And so I think this is the area where I'm less familiar, and I'm curious what, based on what we've just discussed, how you see it.
Yeah, so you could I agree. Those are potential places where you can use it if you have trust issues with an operator, right? I mean, that's a key that's a key thing, right? And in this case, are it's like, is everything that you're taking in, right? So if you look at the first one, the abstraction layer, right? If you think of a traditional API gateway, right? Can you prove that all requests incoming that pass, let's say an access control layer, are passed into the middleware logic, right? So in other words, there's no censoring, right? So you have a proof of censorship resistance minus any access control rules, right? And you can even then prove that the access control rules were appropriately applied, right? I mean, you can basically, every single code execution could be verified, and you could pass that along, and basically verify the entire stack.
To me, that would be the holy grail.
Yes, I mean, you would, yeah. So it's like, but the question is, it's like, where's the, what's the effort versus the output, right? I mean, it's like, or that you need to do, if we are talking about. So I could see that, it's like, if you think of an application of RISC Zero, where you are settling in the Fed overnight window the outstanding, somewhere between $5 and $8 trillion worth of settlements, and that is done correctly. Right now, everybody trusts the Fed that their mainframes operate correctly. Right, and basically everybody just says, yeah, I expect this, and this is out. So everybody validates independently that they're not being cheated, and there's like, or at least they pretend to, but there is no collusion resistant way to prove to the outside world that even though you don't see anything, there's no collusion going on, right? So similarly, you can then think of this as a, if you put this as, if you're settling invoices, right? Orders versus invoice order versus invoice matching, proper application of taxes, all of this stuff in a not only that the two sides, right, which is the key thing about baseline, is the synchronization of two systems of records, right? And the idea is that the proof that is then verified on chain is proves that, right? But there are a whole lot of trust assumptions that are sort of like implicitly baked in, and the only thing that you're really proving is that given the state that everybody has agreed upon, the state transition is done correctly, right?
Yeah. Well, it's interesting to think about how could you do multiple parties. So for example, things like tax collection, make sure, because the amount on the invoice, you may have agreed upon pricing, but then there's tax on top of that, and you won't necessarily know ahead of time, or it varies based on jurisdiction or tax year or whatever. And you could actually plumb all of that through.
Yes, I mean, you can prove to an auditor and to the tax authority that the tax was calculated correctly.
Yes, well,
without revealing.
And to the purchaser, you say, yeah, you charge me this amount of tax. And you say this is government tax, but it's different from last invoice, and you could automatically validate that all the way through. So you know that I, as a purchaser, would know that I'm paying the correct amount. You're withholding the right amount of taxes.
Yes. I mean, that's, yeah. It's a proof of correct execution of the tax line and everything, right? So it's based on the current state, right? Are all the discounts or the penalties applied properly, right? Are there any outstanding credits from a previous invoice, right? That you typically haggle about, right? But if you don't, if you do this consistently, then there is a you have a synchronized state. There's no dispute, right? So the whole thing about baseline is about ensuring that disputes are either completely obviated or significantly reduced, right? And that, and the level is entirely dependent on basically the level of validation you can implement in a baseline protocol implementation. right? And that both sides are comfortable with.
It's interesting to think about in the long term, you could end up in a situation where, as a company, your books, you'd actually know you'd have integrity guarantees on the transactions coming in, as well as internally. So you'd have a lot of confidence that you weren't going to have to reach back and restate, because one of your vendors screwed something up or one of your suppliers.
Right. At that point, so that actually brings me to a question. It's like the challenge here is you need recursion.
Right. So you do.
So that leads me to the next question: is your recursion friendliness?
Yeah, so that's a great question, and we've actually just been very actively developing recursion mechanisms. It's obviously very challenging, but we currently have like a recursion circuit that recurses inside our own proof system, produces one proof out of two proofs in about 2 seconds on a MacBook, and it's just barely done. And then we additionally are working currently on the ability to take one of our Stark proofs and emit Circom proofs for it. So if for some reason, however you're settling this, or wherever you need to actually record the proof and verify it, oftentimes snarks are a lot friendlier than Starks, especially in the Ethereum kind of context. So so the circuit's very recursion friendly at this point. That stuff's not quite open sourced yet, but we will be open sourcing it in the future.
Yeah. So that gives you that's part of being able to run from a developer friendliness angle. It's part of being able to run more or less arbitrary programs, and that if they you don't have to run the whole program at once, you can chunk it up and you can use recursion to roll up,
as well as add state. You can actually add statefulness using this mechanism as well. If you think about more like Amazon, I can't remember what they call it, their stateful function workflow graph stuff, which is really interesting, I think, using zk to kind of run up to a certain point, pause your sort of business logic, and then react as new information comes in.
It's also relevant for supply chains, right? In the end, you want to be, you can prove an entire supply chain with one proof.
Yes. Yeah.
Definitely.
And there are other applications that have the same shape that we think are super interesting.
So the question, and this is maybe a little technical. The big challenge is that there are two challenges with recursion. One is the size of the proof carrying data, as well as with as you carry forward, right? The size of the proof carrying data as you start to add recursion levels increases, right? Because you need to increase. You're adding basically all your conditions, right, of the previous proofs. Otherwise, you can't prove it in the same circuit, right? So the proof carrying data by definition has to grow, right? And
although it actually reaches a stable point, and pretty much maxes out at about like 400 kilobytes. You could in this proof system at least, and at least at zk Summit, this year, which is why I'm like in Lisbon right now. There's a lot of research coming out, about how to minimize the amount of proof carrying data, and the amount of proving time in between all of these different steps. So you see all these folding schemes coming out now, as well.
Yeah, this is important. Which the folding schemes require new curves, right, with different bit sizes, because you're basically you're folding one onto the other, and you can't do bilinear mappings. So that's not allowed. So you need to, right? So you need to have more cycles.
We actually use a Stark.
Right, so you have to have more cycles in your the group has to be larger, but it needs to map onto the same. The problem is that if the the problem is the group size, right? It's like if you're
Well, so
doing
to be clear, we
cycle
use
friendly.
we use Stark construction, so we actually don't use elliptic curves at all.
Understood. You're still using you're using FRI, right? But it's still you're using you still have
the way we
constraints that you're carrying
it's
forward.
True, but the way we've implemented the recursion circuit is actually just as its own circuit, and the constraints are basically fixed. So the size of the Stark proof grows up to a certain point, but then it stays the same.
Right.
Yeah.
So,
yeah.
but
so because it's a VM,
yeah, but you can't do that with general proofs with general prover systems.
You can, yeah.
Right, because the proofs vary, right? It's not just the same one.
Well, but it is, because the proof is actually of the VM. So in this case, the circuit is the RISC-V chip. So the data is the program. So the circuit is actually the same. Yeah. So it totally works. And you can basically, recurse a billion proofs into one, and it will not be any bigger than 16
yeah, sorry, that makes sense. But it's still a question of how big your, does it fit into 64 bits, right? I mean, what the level of security that you have, can you break it down into everything fit into 64 bits, or do you have to have more cycles, CPU cycles to process the field?
Yeah, so it's probably, we use a slightly different field than everyone else. Actually, we use something called we call it Baby Bear, and it actually fits into 32 bits, and then we use a 4x expansion field to achieve the 100 bits of security that we typically target. However, these things are fairly parametric, so I think that's actually an interesting point for lots of enterprise use cases, is that the desired and needed level of security could be quite different depending on the use case.
Right.
For public blockchains, you obviously need very high security, and because you clearly don't want to be able to falsify a public record. Even if it takes you a year to break something, it's still broken. But currently, the general mode our proof system runs in, we actually have 100 bits of security, and typically we also support SHA-2 or Poseidon. But generally, you can sort of pick which hash function you want to use as well. Although you do have to implement those in a circuit. So yeah, a lot of the sort of problems of getting a ton of proofs for general purpose computing down into one proof are actually mostly solved at this point. For general proving it's for general purpose
computing, if you're proving the execution trace of your, if you're just proving the execution trace of your VM, right?
Mm-hmm.
Yeah, I'm glad, Brian, you're here, because that's a layer deeper than I go. But
yeah, well, I'm still not Jeremy, so I'm definitely not. So Jeremy's not here right now; he's in the air, but he's our chief scientist and the inventor of the proof system. Obviously, our work, we stand on the shoulder of giants, many. But it was very fascinating to see all of the different approaches to proving system optimization that people are taking nowadays. At ZK Summit 9 really blew my mind this year.
But Andreas,
the capabilities of these systems are going to really increase over time.
We're pretty focused on being able to do as much as possible in software, write business logic and software, compile that down, and have developers never have to think about the circuitry underneath.
Yes, of course. That's you don't want to do that.
Although there's some discussion about how do we do extensibility in a way that maintains compatibility? Is there a way that we can make it so you can bolt on an accelerator for a particular operation that you need, if you have if you're not just a normal application developer, but you have some exotic algorithm, there's one step that really gets a lot more efficient. Is there a way to bolt that on and then have that not break compatibility with all other instances of
so
that's all hypothetical.
That's basically also solved at this point. But anyway, we don't need to get super far into the nerdy depths of the zkVM unless you really want to. But yes, we do have like ways to build acceleration circuits for like ECDSA. So we actually just built a big int accelerator so you can do very large integer math in a way that doesn't sort of incur the overhead of decomposing it into RISC-V 32-bit integer operations.
Yeah. Now, going the other direction, what are the interesting languages in terms of?
So we do have a question from the chat, actually, that Zonal just posted. And the question is, like, what are our thoughts on composable ZK? And how do you make your offering approachable for supply chain system users? So I think composable ZK is.
And Chung, we can still see your
no,
chat.
No, sorry, Chung, your screen's still on. You might want to stop sharing.
Yep.
No, the chat window.
Drama.
Yeah. Sorry. Yeah.
Thank you.
So composable ZK, I think, is a critical trend, and we actually have an open source user actually did this a while ago. They verified Cairo StarkNet proof inside RISC-V by just importing the prover, and so you can actually do that in a lot of instances. You can import other proof systems and run them inside different proof systems, and then produce a different proof. So, for instance, as I mentioned earlier, right now Jeremy's implementing a Stark to Snark conversion system, basically. So we will be able to you can recurse all of these general purpose proofs down into one single proof. That's the 400 kilobyte Stark proof or whatever, and then you can actually run that through Circom and produce Gross 16 proof, or you can use FLONK or FFLONK. I'm not sure what people are calling it. Yeah, so I think that being able to do that is actually really important because all these proof systems have really different properties.
Yes.
And so I think how we're planning on making our offering approachable for supply chain system users. Well, I mean, the main way we're planning on doing that is by letting people use the code that they already have for sort of settling transactions or comparing, insurance claims, any of this stuff that you should generally be able to use, if not exactly the same code, a very similar algorithm in something else. So users shouldn't generally need to think about this, although, at a certain level, somebody needs to be able to like security architect the entire system, clearly. So, yeah. At some point, I expect JVM code to be running on this system.
Yeah, I mean, there's a big benefit to bringing battle-tested code that you've been running for a long time over rather than re-implementing.
Well,
don't
it's
tell
also possible.
Don't tell it to the banks, otherwise they'll go, oh yeah, here's my PL SQL. Have fun with it.
Yeah, no, I'm sure they will.
We
I think that's like actually a.
You're way too young for that. It's like the AS400 existed before you were born. So like sign on and Lanza for the web and COBOL and all that good stuff. But that's what most of the financial systems still runs on.
If someone wants to run COBOL on zkVM, we can make that happen. I mean, that is a if there's a code base, and it's like, well, you could rewrite it, obviously, like you rewrite it in C or Rust or something, or you could port the COBOL compiler. Like it might be easier to port the compiler.
Oh, you don't need
you
probably don't need to port the compiler. You just need to make the compiler spit out RISC-V check. It's pretty straightforward. It probably already works. You can probably just already compile the RISC-V. I'm curious now, and I'm going to look. But I'm really curious to hear from all the baseline people.
One more.
As I was doing.
One more question in chat, actually. So Emily asked, how does the flow work with RISC Zero with EVM on chain? Is there an example code to try that proves Ethereum state? So
there's
that's the other direction.
Right. So there are two ways that you can use sort of RISC-V in an Ethereum context, and one of them, so being able to take programs that are run in RISC Zero and prove them on chain in Ethereum, that's actually the bit. You could do that right now. It would just cost a lot of gas because the Stark proofs are so large from the recursion. So that's why we're building this Stark to Snark converter. So once that's done, you will be able to basically take one of these general purpose programs, You can pass in the state from the EVM. This is why I can find the link to the sort of proof of assets work that people have done, where you basically pass in your program. In this context is like REVM, and you pass in a block state and your key, and prove that you actually have up to N million dollars in assets without revealing where they are. So that's one way to do that. And we will also be building this bonsai system that will let people submit proofs, requests for proofs into the system, and then we'll roll them all up and sort of pay the costs across Ethereum. But that's useful across sort of enterprise applications as well, not just public blockchain. So sadly, there isn't an example code. There's example code that proves Ethereum state. You can look up ZK proof of exploit, or I can find this proof of assets thing really quickly. So there is example code for that, but there's not example code for proving RISC Zero state in Ethereum, if that makes sense.
Yeah, no, it's like but you can prove the zkEVM output, right? The bytecode execution, right? Yeah. Because you're
yep.
So this is then, at the you don't have a compiler for that. You're just doing the bytecode conversion, right? You're just running
yeah, basically. I mean, you're just actually really, you can choose your EVM. I don't know that we have Geth running yet, but we do have, like, people use Sputnik or REVM. So you can actually choose the client, the specific client that you want.
Oh, yeah. I mean, REVM, yeah, you can do right away because it's in Rust, right? So it's like it's like that.
Yeah, exactly. So that's what this example I just pasted in the chat is basically proof of assets using REVM, and you can see that the code's like not that complicated. I don't know how far along this project is, but yeah, it's pretty well thought out, and I think it works.
So the interesting thing, and Vitalik also posted about this, right? Is that you're actually reducing you can reduce the size of the chain by doing exactly that. You're running all the transactions. You don't need to keep the transactions anymore. You just prove state and state transitions, and then you're posting that. Just the chain becomes just the recursive proof. So it's like
basically what Mina has been doing for a long time.
What Mina has been doing, but it's like maintaining state. So the point is that you're still stateful, right? So and that was the original question, is who maintains state, right? So the validators still maintain state. It's just that all the proofs it's all compressed down into proofs, and no one needs to maintain the state except the validators, right? The validators maintain the explicit state, right? Because if you're going stateless, then you really have then you have the unsolved problem of race conditions, right? Because I need to update the overall state, and then if my update impacts another person's update, and what's the sequence, what's the right sequence, right? So then
of course, and blockchains are very good at figuring that out, right?
Right, but it's like that's hard because you don't have sort of like a central ordering mechanism in a that the nodes provide, right? You're basically just every user needs to have maintains the state, changes it, right, and then posts it, right? And it's a valid state transition, right? But is the state transition valid because it if another one has impacts the same target account, right? So
it doesn't solve consensus for you.
Alice and Bob send the transaction to Claire, right? Basically the same one, like pennies, right? It's like one of them will fail.
Yeah. Well, and I think if you follow that thread, you need global consensus. You still need
you still need consensus, but the problem is that the users don't know what the consensus is of the state that they need to base their proof on, right? They generate the proof, right? They're generating the state transition, and they're just sending in the proof, right? And it's but the point is this, like, it's like if you're impacting the same account,
you could still have like all kinds of we're not explicitly solving all of this. It seems like
right? No, but that's a general problem for stateless, for if you want to have a stateless consensus-driven system. A stateless distributed system requires that all the users maintain state, and then you have then you're automatically getting a race condition issue that is
Totally.
not solvable, except for certain transactions will just simply fail.
Yeah,
because one is processed before the other.
There was another totally. There's another question, Sonal. I think we've
Yes. So John Wolpert, one of the OG baseline leaders, who's a product exec, has the comment that there's very little on the site referring to blockchain on RISC Zero's site. The current discussions seem to indicate an Ethereum focus potentially, but he is interested in learning about the choice of not putting blockchain front and center on all of the collateral, as well as interested in learning if this can be used without a blockchain.
Yes. So part of the current sad state of the website has just been, it's taken a while for us to get our sort of branding in a state that we really are going for. That's hopefully going to be resolved pretty soon. So, we're big believers in blockchain and blockchain technology, but, our background, I would say we're fairly new to the space, at least the co-founders are. So, we do think of this technology as much broader than blockchain itself, but we are very much focused on the blockchain side of the world. However, we also, this Bonsai network that we're building, Bonsai is intended to be more of a sort of public good and network rather than a company effort. So we see RISC Zero as building that, and so Bonsai will really be where we focus most of our sort of blockchain story. Yeah, but we have been talking to various other teams about things outside of the blockchain context. Chung, I don't know if you want to talk about that, but it's certainly come up in conversations that even the limited amount of blockchain that we mentioned on the RISC Zero site does occasionally cause concern in certain quarters. So
yeah, I think there are a lot of applications outside of blockchain where like baseline, which sort of sits certainly outside of DeFi, and like baseline sits in between enterprise and traditional blockchain, and we don't want to neglect that side of the company, or that side of the potential applications for ZK. And zkVM specifically, because of how we've designed it, could fit relatively well into existing software where it can be a security add.
The key here is really that you want to be able to have these synchronizers either between two or more parties, and that they basically take advantage of the security properties of a public chain. That's the primary thing. So anybody can validate anything at any time without, it's basically a great way to ensure public transparency of things that would normally not be made transparent, or that are supposed to be transparent in like 10K or 10Q filings if you're in the US, or whatever other public record filings publicly traded companies must do. It also would help to create more trust in other entities that do not have public record requirements filings, but they could do that now in a way that doesn't reveal anything, but still can say, hey, we're not like cheating anywhere, right? Which is also, again, kind of important if you're like tax authorities, again, they can, or regulators, they can now say, oh yeah, you actually are implementing data privacy properly. You're actually you're implementing KYC AML requirements properly. Not on chain, just generally speaking.
Yeah. I think that's a huge class of use cases for ZK in general is going to be sort of like having some trusted bodies say how these things are supposed to occur, and people be able to actually prove that they were doing these things correctly in any kind of context.
aggregate that data in a good way. So
Yeah,
you
I
can
know,
say,
like
hey,
the person,
like ESG goals, my company, 27% of our revenue comes from, this category of vendor that's a little better in some ways than the general industry. And you could actually roll that up and report that in a verifiable way.
like proving that various insurance claims or whatever potentially are following whatever rules they're supposed to, things like that. Very interesting. Yeah, I will say, I don't know, someone, are there other questions, or can I have this?
Yeah.
When I sit around and think about the utility of this technology, I started, occasionally really getting into this idea of solving supply chain stuff en masse, and really enabling people to communicate orders more effectively for various, bits and pieces of all kinds of things like housing supplies and building materials and complicated parts and all of this stuff. So I'm curious where this seems like sort of where Baseline started, and have we seen any traction there? It seems like a really hard problem to solve, and it's probably going to take the industry a while to get there. But
the problem of
the
adoption,
sort of,
right?
Radish 34 stuff was like really interesting, but it does seem hard to get people to adopt it.
Well, yeah, and I think a lot of us had been veterans of a lot of failed blockchain or enterprise focused blockchain projects, and really just kind of sidestepped or blatantly ignored the critical questions of where is this going to sit within the architecture, and does this mean that I have to give up my ERP system or my CRM, because I'm not going to. So Baseline was a way to actually come out and say, this is a way that use your existing systems, but just prove consistency. Just prove that everybody is working off the same data set. And it didn't involve cloning and moving it to some central repository like a blockchain, which is also a massive threat surface for any hacker that wants to, come in there and pick some locks. And, really where it went from there. Zero knowledge is an interesting aspect right now, and when you socialize it a lot, you kind of have to cross that gulf between, I'm not sharing data objects with you, I'm sharing proofs. And because I can't share the genuine article, I'm either prohibited by data privacy or just by competitive position. I can't share it to you, but I need to prove to you that I know the secret. And you need to be satisfied that I know the secret, and getting those elements there is requiring a lot of gymnastics, at least conversationally.
Yeah, definitely.
The method that I've been using recently, just trying to demonstrate a zero knowledge exchange, is say, Brian, I want to prove to you that I know your phone number, but I can't tell you because somebody might be listening. Somebody might be, looking in there. So I can't say the 10 digits. So what am I going to do? I'm going to pick up my phone and I'm going to call you. And if your phone rings, I have proven to you that I know your phone number. And I have given you no additional knowledge other than I have proven it. So
totally.
That is
That's a good example.
Huh?
Oh, yeah, great example. I go ahead. I did want to talk about an emerging thing that might be of interest to the audience, which is the viability of zkML. We're not super focused on that, but we've actually seen some of the latest research, people being able to prove things about data without revealing the data by using a machine learning inference model inside zk. So I'm personally optimistic that over the next 3 to 10-year time frame, people will be able to actually prove things about what they want ordered or various aspects of their company operations in ways that can give people confidence about their operations without necessarily revealing competitive or proprietary information.
Right. A lot of people sit there and say, I need to be convinced. You have to show it to me before I believe it. And I'm like, well, I can't show it to you, but what I can show you is a mathematical proof, proving. And I'm not just attesting, and you're not taking my word for it. I am proving that I'm working off the same secret that you are.
Right. Like the crazy example I came up with in my mind is, say you had a very complex part and you wanted to place a large order for it that was going to take up a lot of some factories, very expensive CNC machines for a long period of time. and they don't want to necessarily commit that capacity to you without proof that you actually need it. So you could actually provide at some point, proof of similarity of a part without necessarily like, oh, this requires the same number of G code steps and retools and all of this stuff without necessarily revealing the part. But you could prove that your demo part is effectively like toolpath equivalent, which is pretty nuts.
Actually, turning it around is really critical, by saying, I need this at this point in time, or is it actually available, right? Because right. that is much more, it's like, can you produce this deal, right, in this amount at this quality at this point in time, by this point in time, and deliver it, right? So this is obviously hard in the physical world, but in the digital world, it's much easier. And it's actually very, very relevant for actually what we're doing right now, right? Because what we're doing is we're utilizing probably 15 different carriers to deliver data on demand, right? It's like my feed runs through like AT&T, and that is, but Brian, you're in Portugal, which means the data that you're seeing right now the feed runs from the Zoom servers through their providers to probably through a wholesaler to your local ISP, right, in Portugal. So you have a whole data supply chain that must work, but that means the inventory must be available, the circuits must be available, the capacity must be available, and that's actually a huge coordination problem that currently exists in the telecom industry. And in fact, like Sonal and Mark and Keith can talk about that, because we're actually working with in that telco space right now, where we're working with companies there to solve that coordination problem, right? So commitments to inventory,
like more
availability,
approachable than the physical world stuff right now. Yeah,
right. So it's that's more doable, where you're then committing to certain things to be available at a certain period of time and paying penalties if that inventory is not available, right? Because you committed to it, you got to commit that prove this is available, and then if it's not available, right, you can prove that it was not available at that time without revealing anything. That's crucial, and you're opening the commits, and that's it, and you can prove that it was correctly executed. So that is a very, very, so the quoting and ordering and then delivery, right? That entire lifecycle orchestration across a data supply chain, right? Or connectivity supply chain is a huge problem, right? So this is a $100 billion plus market globally that has massive problems when it comes to
when I think about it as data supply chain, your packet supply chain.
Yeah.
So it's like,
real. I hadn't really thought about it, but yeah.
Connectivity supply chain basically is like data on demand, right? Is it there when it's on demand? Are the circuits working? If a circuit is not working, who's at fault? Yeah. Right? Because then you have, do you meet your SLAs? Do you don't? Are there credits then on the invoice because you're billing bulk? Right, so it's that goes through the entire life cycle, from quoting to ordering to delivery to invoicing.
Well, actually, it seems like now that you explain it that way, every commodities market starts looking a lot like that. I mean, data capacity is probably the most ephemeral commodity on the planet, but electricity or water or grain all have a similar shape.
Correct.
So Sonal rightly points it out that we're about out of time, and we want to pull it back and briefly sum up, how RISC Zero can sort of help realize the the ambitions of the baseline project. And I think there are two ways, and that's to make proving the sort of execution layer. I mean, Chung pointed out there are 3 points in the stack, but there are places, in the sort of core execution framework where you can use RISC-Zero to plug in existing trusted code bases. I didn't really touch on that. It reduces the audit surface a lot if you can just have a little tiny ZK chip and then use code that somebody else already audited, rather than needing to re-audit circuits, which there's not a lot of speaking of supply chains, there's not a lot of audit capacity for circuits. So, RISC-Zero can, by using that and using pre-audited code, can simplify sort of code compliance mechanism, like complexities, at pretty much all levels. And then additionally, I think the part that I find really interesting is the potential to write interesting kinds of ZK application logic and let counterparties prove things to each other about about whatever was done without revealing exactly all of the data behind it.
So to wrap, we have an interop demonstration coming up. So interop between two different baseline implementations, baseline protocol implementations coming up around. There's a working group around that. We have a use case, which is synchronizing banking data, which is a huge problem globally, right? So currently our approach is that we're, one side generates a proof and then sends the proof over to the other side without the public input. And the public input is just a root, right? And can you generate, if you're proving synchronicity by being able to generate the root and verify the proof.
Cool.
That's a very simplest. That's a simple thing. However, I think there might be some interesting synergy there if RISC-Zero wanted to like participate and maybe make that a bit more extensible on at least one side.
Love to dive into that. Yeah.
So we have a regular meeting Fridays at 7 a.m. Pacific. And if one of you guys wanted to like sniff in and see whether they want to participate, there's also an RFP that is out that, organizations can participate. We're raising funds for that. So, you can, funds means either dollars or in-kind contributions that work, that work too. So happy to take that discussion to the next level, and if you're interested, we would be happy to incorporate, a zkVM in this
Cool.
use case.
Yeah.
Yes.
We'll definitely pop into the call and would love to, coordinate on that. And just wanted to say thanks for having us on and for working on this like wildly ambitious project.
Yeah, thanks for joining us. We'll see you on different work group calls, hopefully, and feel free to join us on any future baseline shows, including a part 2 for RISC-Zero. All right. Thank you all.
Thank you.
Wow.
Thanks, everyone.
Cheers.